Hey everyone! Today we're going to be creating an ERC20 token and deploying it live on the mainnet. There's going to be 3 chunks here. First is a quick setup part where we just create the directory, install the dependencies that we need. Next is going to be a part where we actually code the contract using interfaces from OppenZeppelin. And then finally we're going to go through everything that we need to do to deploy the contract live on the mainnet. So starting with the setup part, we're going to create a project directory and run the code that we need to run to install all the dependencies for this project. I'll talk about these dependencies more as they come up throughout the project. And then we're going to code the contract. Using interfaces developed by OppenZeppelin, I'm going to go through the parts of these that we need to understand in order to know what's happening in this contract. And then we're going to create our own constructor, our own mint function, and we're going to be using access controls so that the minting stays controlled, but also flexible if we want to add more use cases later on. Once we develop the contract, I'm going to go through all the steps we need to go through to deploy it so that anyone can use this token live on Ethereum mainnet. We're going to use Hardhat to streamline the deployment. We're going to use Alchemy as our node operator. We're going to verify the code on Etherscan, and this lets anybody view the code that we created and interact with it through Etherscan. We're also going to use Web3.js to create an account, which is needed for deployment, and we're going to use .env to store and retrieve our private keys in a way that balances kind of security against the need to have private keys available through development. If any of this sounds new to you, don't worry. I'm going to go through everything in the details that we need to implement it and in the details that we need to understand what's happening throughout this project. So as you can see, I'm in a folder called Solidity. In here, I'm just going to create a new folder, and I'm going to call the token Mac Ventures token, and I'm going to name the folder same as the token name. So Mac Ventures token. And you can see that now this folder is inside of this other Solidity folder. I'm going to cd into the new folder, and I'm going to open VS Code from here. You can follow along in any IDE. Later on, I'll also create tutorials on how to install VS Code along with this code shortcut for it. So now we're in VS Code. I'm going to open a terminal window to continue working out of here. And you can see that we're working out of this Mac Ventures token directory. So the next things to do are to initialize npm. And I'm just going to accept most of the defaults here. No description, no test command, no get, no, none of these things. Yes. And that creates the package.json file, which will be updated later, not manually though. And then now we're going to install all the dependencies that we'll need. So npm install save dev hardhat. So this is going to install Hardhat, and it will save it as a requirement. And it looks like Hardhat was installed. Next is installing Web3, which we need in order to create an account to deploy the contract. Save dev web3. And so it looks like that was installed successfully. So the last thing that we need is .env to manage our private keys. So npm install save dev .env. And that was installed successfully. All right, so next we need to initialize Hardhat. So npx hardhat. And this is going to ask us a few questions. Since we're just creating a simple token here, I'm just going to say create JavaScript project, and also just going to accept most of the defaults here. A get ignore is important, especially later on when we work with managing private keys. But this creates one automatically, so we don't really need to create it manually. We can edit it later on as well. And then for everything else, I'm just going to accept the defaults. And it looks like the project was set up successfully. So this creates a few things that we don't need. We don't need this lock.sol, so I'm just going to delete this contract because we're going to create our own. We do need deploy.js, but we'll create our own version. And we don't need this test file because we're not going to do any testing in this tutorial. And the last thing that we need to do is install the OpenZeppelin contract interfaces that we'll be using to kind of bootstrap our contract. So for that, it is npm install, and we're going to reference it with OpenZeppelin. And it looks like that installed successfully. These high severity vulnerabilities aren't too important. Most of them are involving use of a randomization method, which we aren't going to be using in this project. So now we're going to create the contract. Just going to create a new file under contract. I'm going to call it Mac Ventures token.sol. VS Code is going to do some kind of smart text highlighting. That's because of an extension that I have installed that I'll cover in the setting up VS Code tutorial that I'll do later on. I'm going to start off with just some code cleanliness, so saying where this file is, under contracts, ventures token.sol, identifying a license. So solidity files start with a pragma, which just specifies the version of Solidity that the contract is written under. And this contract is going to be using version 0.8.17. We're going to import two things, but I'm going to start with one, just to keep the tutorial easier to follow. So import So this is importing OpenZeppelin's ERC20 interface. Let's dig into what that actually is. So if we go into node modules and find OpenZeppelin and follow this path. So token and then ERC20 and then open up ERC20.sol. So this is a kind of bare bones implementation of ERC20 token. We could create a token, we could almost create a token just from this. The only thing is that this does not specify how the tokens are created. It doesn't talk about the logic behind minting the tokens. There's a lot of stuff in this script, but the ones that we're going to be using are their constructor, which is defined right here. This is a very simple basic constructor. All it takes is the name of a token and the symbol for the token. So let's go ahead and do that. So this is the format for creating a contract in general. You say contract, the name of this contract, and then this is inheriting everything from OpenZeppelin's ERC20 .sol file. So everything that they've implemented here is going to also apply to Mac Ventures token. Contracts have a special function called a constructor, and this gets run once when the contract is created. So since we inherited from the ERC20 contract, we can use its constructor like this, passing the token name and token symbol just like this. Cool. Another thing that I want to do for Mac Ventures token is give it an initial supply as an input to its own constructor. So for that, it's going to be a unsigned integer. And we're also going to code this so that the creator of the token gets this initial supply when they create it. So we're going to use the internal mint function that's inherited from OpenZeppelin's ERC20 contract. So let's take a look at that function now. So we're back inside of OpenZeppelin's ERC20 contract. I'm just going to search this for mint. So this is the function that we're calling. It takes an account, sometimes called addresses, and it takes an amount to mint. It's internal, so the convention is to start internal functions with this underscore. Internal just means that it can only be called from within this contract. So nobody outside of this contract can use this mint function. And it has some logic here for security and for tracking balances. So for example, when someone calls this mint function, minting to an account, the amount that they mint is added to that account's balance. And it also increases the total supply by the amount that was minted, which makes sense. That's kind of what minting should be by definition. It also emits a transfer event, sending from the null address to the account that someone supplies, the amount that they supply into this mint function. And it has extra logic to call other functions before or after the token. We're not going to be using any of that here. So in our case, we want to mint to message sender, which is a message is kind of a special object that gets passed anytime somebody calls a function on the Ethereum network, and sender is the ID of the person calling the function. So what this is saying is that we're going to mint to the person who creates this token, and the amount that we're going to mint is the initial supply. But there's something a little bit confusing in Solidity. Solidity doesn't really represent decimal values, so instead we have to scale everything up by the number of decimals. So here I'm going to say times 10 to the power of decimals. And what is decimals? Well, decimals is also part of this ERC20 contract. And it is defined right here as 18. And it's possible to override this. So for example, USDC only has 6 decimals. You can really set this to kind of whatever number you want. I'm just going to stick with 18, which is the default, which is also the same number of decimals that Ethereum has. So in the end, this is saying the person who sends the transaction that creates this contract will be minted the initial supply, and then it just scales it up by 10 to the 18 to put it in units that the Solidity contract works with. But what they ultimately receive in kind of a human readable scale will be this initial supply of tokens. And the next thing that we want to do is add access controls. So I'm going to import an interface for that from OpenZeppelin. And so this access control contract that OpenZeppelin maintains gives us the power to define specific roles which have access to specific functions within this contract. And so I'm going to create a minter role, and then I'm going to give it access to mint tokens. So, and the guidance from OpenZeppelin is to store this as a hashed value. To do that in Solidity, we're going to use this function. And so this is just defining a new role that is public, so people can query this role from the contract. And now I'm going to create a mint function. And it's going to be a public function. And since it's a public function, that means that anyone can call this function. So we actually don't really want that, because that would mean that anyone can create these tokens for free, which is not a healthy thing for a token. So we're going to restrict this function so that only people with the minter role can use this function. And the thing that we're going to let these minters do is call that internal mint function, passing it an address that they want to mint to, and the amount that they want to mint. So why might we want a mint function? One way to create a token is to fix the supply, which means that there is no mint function, so no more tokens can be created. Here, having an ability for the token to be created, and having the flexibility to assign that power to create the token to new addresses or to new contracts enables a lot of possibilities. So this means that lots of different contracts can be created, and those new contracts can be granted this minter role. So for example, people might create contracts for staking, where somebody would deposit these tokens into the contract, and then the contract would be able to mint new tokens to them as a reward for staking their tokens. People could also create a virtual exchange contract. So that would enable other people to deposit other tokens to this contract, and this contract would pay them in these tokens from a newly minted supply of these tokens. It could also enable a bonding contract, so someone could code up a new contract that accepts other tokens, and over time slowly mints these tokens to the people that deposited into that new contract. Or like Ethereum and other proof-of-stake tokens, somebody could create a new contract that mints tokens to the miners that process transactions for this token. So that might lead to quicker transaction speeds, or miners otherwise being incentivized to prioritize transactions that involve this token above other transactions on the network. So having this mint function and having it gated by this specific role leaves open opportunities for other contracts to create more of this token if they are granted this role. So how does the granting of a role work? Well, let's dig into OppenZeppelin's access control contract now. So that is under contracts and access control.sol. So this is another very big contract, but the important parts of it are this kind of description about how roles are created and revoked. Specifically, there's this default admin role, which has the ability to assign other roles. And then beyond that, the other roles can be very flexible. So we created the minter role, but you can imagine a world where somebody creates a lot of different roles, which gives very fine-grained control over what different entities can do within a particular contract. So we're going to be using an internal grant role, which is defined here. And the importance of this is that we want to give the default admin role along with the minter role to the person that creates this token in the first place. That way, by giving them the default admin role, they're able to either pass that role on to other people or to create new minters as new contracts are built that would require minting. And another interesting thing here is the only role modifies a function so that only the person with that role can call that function. And how it does it is with this internal check role, which assures that the person has that role. And then in Solidity, this syntax underscore followed by a semicolon means kind of continue on with the function that is being modified. So back to our contract. Here in our contract, when we use only role, it checks that the person has the minter role. If they do have the minter role, then it continues to run this function, which is just to call the internal mint function. So to implement all those things that we talked about, we need to use grant role to give the token creator the admin role along with the minter role. And one last thing, I'm just going to leave a comment that I am the author. Actually, one more thing that I forgot to add is inheriting from access control gives us access to these internal get role method and to this only role method. So that wraps up the contract. And the next thing that we need to do is a lot of setup for contract deployment. So I'm going to shrink down node modules. And before writing the deploy script, we're going to modify this config script. So first is a few requirements. The one that's in here by default just requires Hardhat, which is kind of the minimum thing necessary to deploy a contract. We're also going to add a dependency on Etherscan, which lets us verify the contract, and we're going to add a dependency on .env, which lets us access environment variables, which is where we'll be storing our keys. And then in this module exports, it defines the version of Solidity. We're going to add two other things here. The first is something that lets Hardhat interact with Ethereum networks, both the testnet and the mainnet. And then we're also going to add something that lets it interact with Etherscan to verify the contract. So we're going to use the Gorelli testnet, and this takes a URL which connects you to a node that's running this network. For this, we're going to need an endpoint, and we're going to need an endpoint. And since that's sensitive information, we're going to save it in a .env file later on. But to access it in this script, we're going to use the following syntax. This is a variable name that we're defining in .env, which I'll create after this script. but we're going to get these from Alchemy later on, and I'll show that in a few moments. The next thing that we need is an account, and this is an Ethereum account, which we'll also be creating in a few moments after this script. So this is all we need for the Gorelli testnet, and we're going to do something similar for mainnet. So once we get these endpoints and create a private key, we'll be able to use this to deploy the contract on testnet and mainnet. One thing I forgot to specify is that these are the networks. And the last thing that we need to add is a way for Hardhat to interface with Etherscan to validate, to verify the contract. This just needs an API key. And so this Etherscan API key we can get from the Etherscan URL here. These node endpoints we can get from Alchemy. And in order to use the Gorelli test network, we're going to need some test Ethereum, and I'll show you how to get that from this faucet. And then, of course, on mainnet, in order to deploy the contract on mainnet, you're going to need to fund your wallet with Ethereum. One way to do this is to first buy some Ethereum on a centralized exchange and then send that Ethereum to your account. So this file has a lot of sensitive information. It has 2 enter points, it has an API key, and it has private wallet keys. One way to store this information while you're doing development work is in a .env file. So I'm just going to create 2 files. One is the .env file that I'll be using, but not showing during this tutorial. The other is a .env public file, which has the same setup as the .env file, but it's something that will be public so that you guys can easily follow along. And since these things have sensitive information, if we're working out of GitHub, we don't want these to become public when we commit code to GitHub. That's what this git ignore file does. In git ignore, you can tell it which files to not commit to GitHub, and you should include this .env file so that these private keys don't get shared outside of this project. So yeah, the keys that we need for this project to work are an Alchemy endpoints for the testnet and mainnet, an Etherscan API key, and a private key that grants access to an Ethereum account. These Alchemy endpoints can be obtained from Alchemy here at this URL. This Etherscan API key can also be obtained from Etherscan here at this URL. And for the private key, there's a few ways to do this. One way is to use MetaMask to export your private key, and then you can copy and paste it here. Again, you want to make sure that this is not being shared outside of your computer. And you'd also, since you're pasting the private key in a file, you'd probably not want to keep much Ethereum in this account just in case this file gets compromised. Another way to create this private key is through the Web3 library, which we imported, and so I'll show you that in a minute. So first, going to that site to get Alchemy keys. I've already created an Alchemy account. You'll probably need to create one for yourself. And I already have 2 running apps. One is an app on mainnet, another is an app on the Gorelli testnet. But it's pretty easy to create apps. You just hover over this app thing, click create app, and you specify the name of the project, a short description of the app, the chain. They have lots of different chains, but we're using Ethereum today. And the network, which could be mainnet or Gorelli for the testnet work. And then once you create an app, you'll be able to click this view key, and it will show you the endpoint. It'll show you a few things. It'll show you the key itself, and it will show you different versions of the endpoint. The one that we're going to be using in this project has a format that is something like this. So it'll be HTTPS, eth-gorelli for the testnet, galchemy.com v2, and then your key will be appended at the end of it. And for the mainnet, it'll have a similar form, just it'll say mainnet instead of Gorelli. I'm not going to show the Etherscan version of this, but it's very similar. Just go to this URL to get an API key, and then once you go through the steps, they'll show you a key, and once you have your key, paste it in here. Again, you don't want to do anything in the env public. You'd want to be modifying. You'd want to create and modify your own .env file. And finally, for the private key, I'm going to walk through how to get this in Web3. If you don't want to follow along with the Web3 part here, you can also use a wallet provider like MetaMask to just say create a new wallet and then export the private key for that wallet. But yeah, so I'm going to create a new folder. And then in this folder, I'm going to create a JavaScript file that we can use to generate public-private key pairs. And in case people are interested, I'm just going to share the Web3 documentation up here. Web3 is a library that has a lot of functionality for creating accounts and interacting with contracts and doing a lot of other things on the Ethereum network without needing a wallet provider like MetaMask. So the first thing that we're going to do is initialize the Web3 object. And then we're going to instantiate that Web3 object. And this takes either a current provider or a local host connection. What this step does is it connects you to a node. It's not too important because we don't even need to be connected to a node in order to create public-private key pairs. Now I'm just going to create the main function. And we're just going to create an account and then log that account to the console so that we can see its public and private key pairs. And we can call it just like this. We can also pass in a string to add entropy. What I'm going to do is pass in a random hex, which just adds some more entropy in this wallet creation process. And then I'm going to use console log. So this will print the information that we get above in the console. And last, going to add main so that we can run this script and see the output. And we should be able to run this with node create account. I had a typo, Web2 instead of Web3, and another typo, 2 5s instead of 1 5. But now that the file is all fixed up, we can run node and then reference this file, and it should print an address along with a private key. And so this private key is what you would add if you want to create a new Ethereum account for this deployment. You would add the private key here. And then the next step is to get some test Ethereum into the account that's associated with this private key. So to do that, I'm going to copy this private key and go to the Grally testnet, which I'll paste in here. So I'm going to go to this faucet and then connect to MetaMask using this private key to show you guys how to get Ethereum in the test network that you can use to deploy the contract to the test network. So here's the Grally faucet. The next step is to connect that wallet to MetaMask. And you can do so by clicking MetaMask, saying import account, and pasting in the private key. So now we've connected 573, EF56, which is 573, EF56. That's how to use a private key to connect to MetaMask. The next thing to do would be to go to the Grally testnet, copy your address, add it here, and say send me key. Now this doesn't work for me because I've done it within the last 21 hours and you're only allowed to do this once every 24 hours. But for you, this would get some test Ethereum that you can then use to deploy the contract and the steps that I'll show you in a minute. So yeah, just emphasizing one more time, don't ever expose this private key. To make sure that it doesn't get exposed when you commit to GitHub, you need to add .env in this gitignore file. And this gitignore file shows all of the files that are ignored when you're adding things into GitHub. Also, just one final way to kind of like confirm that you are ignoring this on GitHub, you can use git check ignore .star. And this will return all the files that start with a dot that are in the that GitHub is ignoring when you upload files. And we see .env, meaning that this file is going to be ignored whenever we push to GitHub. So with all of that out of the way, we can now write the deploy script. And everything that's here is a template, so I'm going to delete probably all of this and start from scratch. Actually, I'll leave this import because we also use that. But other than this import, I'm going to delete everything and start from scratch. Actually, I guess I'll also leave this because we also use this for air tracking. So yeah, we can start off with this template here. So first we're going to create a deployer. Next we're going to log some of the information, like the address that is deploying the contract, which is going to be based on that private key that we provided, and the balance of that address, which is also based on the private key that we provided. And then we're going to create a contract factory, which lets us deploy the contract. And then we're going to deploy the contract, passing along the initial supply that we specified in the constructor of the contract in the beginning. And I want the initial supply to be 50 million. And then we're going to wait for the token to be deployed. Once it's deployed, we're going to log the address of this new token. And then I'm going to add some code to verify the token. This usually fails because it happens too quickly after the token is created, so I wouldn't be shocked if this fails, but I'm going to add some code to verify the token. If it fails, we'll verify another way. And there we go. This is the script that we need to deploy this token to either the testnet or the mainnet. It can be used for both. So first we're going to try deploying it to the test network, and that is npx hardhat run scripts deploy network Gorelli. So there was a typo in the mainnet account, but that shouldn't impact the Gorelli network account. Either way, let's try again. So there was a typo in Gorelli, which might have been the issue. Try one more time. Another issue is that I was using the variable name private key deployer instead of private key. So let's try after that. All right, so it seems to be running. Cool, and so it seems like everything ran smoothly. So what we can do is we can go to this final link in Etherscan. And this will show the token. Going back through, so this is the address that I used to create the token. This is just the balance on that address. This is the address of the token in the test network. So that's what we're looking at now. And then since the part of the code that verifies this token ran successfully, we can also read all of these contracts that are used by this token. And in particular, we can see this Mac Ventures token contract, which is the one that we built today. Cool, so everything looks good. We can also read and write to this token, but I'll try that out on the real one, which I'll try deploying now. So to deploy this token on the mainnet, it's a similar syntax, npx hardhat run scripts deploy network mainnet. And so this is going to deploy the token on the real Ethereum mainnet. Again, deploying from the same address, and it also prints out the account balance in with all decimals. And okay, so this ran, but the verification didn't succeed. So we can go to Etherscan and check for this token address. And the reason I type Etherscan up here is just to go to the Etherscan for the Ethereum network instead of the test network. Searching for the token address. And here it is. So this is the real Mac Ventures token running on the Ethereum network. It was created by this address. It ends in FED, or F3D. And you can see from this address that I funded the wallet about 6 hours ago, and it has this transaction that created Mac Ventures token. We can also check that the balance of the token in this address is what we specified it to be, so 50 million. Go to import tokens. It's a custom token. It's going to be the address of the token. It knows the symbol, it knows the decimals, and add this custom token. Import tokens. And bam, there we have it. The address that was used to deploy the Mac tokens has 50 million Mac tokens. But yeah, returning to this error, the error is around not being able to verify the token. Just going to be showing that what you see in Etherscan, when you go to contract, you just see a bunch of stuff that is not interpretable. So verifying the token helps Etherscan decode this so that anybody can see the code and interact with the code manually through Etherscan. So to verify, the syntax is npx hardhat, verify network mainnet token address, and the arguments that are passed to the token when it's being constructed. And so now it says that the contract was successfully verified. You can go to this link down here to see what is seen on Etherscan now that this contract is verified. And so there we have it. When we go to the contract tab, we can see the source code for the contract. We can read things from the contract. We can write things. So this is accessing functions and making changes that are recorded on the blockchain specified by this contract. And we can see the code that we wrote to create this token right here. And now, so one example for that we might want to do is give an admin role to our cold wallet. So in this case, I'm going to use the wallet that I used to deploy the contract. So that is this Mac token deployer. One with 50 million Mac tokens. And well, first I'm going to go to read contract. And I am going to read the value of the admin role, which is right here. I'm going to manually copy this. I'm going to go to write contract. I'm going to connect to Etherscan through MetaMask. F3D is the account that I used to create, to deploy this contract. And then I'm going to grant role. So I'm going to grant the default admin role. And I want to grant this to my main account, which is macventures.eth. This doesn't work, so I need to, and I'll just copy that from the clipboard. Paste it in here. Click write. It will open MetaMask. From MetaMask, we can confirm this transaction. And then we can copy this address. And if we want to see if the address has the role, we can use this hasRole function to check that this address, which is my macventures.eth address, has this default admin role. And that returns true. Whereas, if we try some other address, it returns false.